Hello everyone, I welcome you all. Now I am going to explain composite wall experiment in our heat transfer laboratory. The main aim of this experiment is to find out the overall heat transfer coefficient of the composite wall. It consists of copper, asbestos, aluminum, mild steel and compare the experimental value with the theoretical value. This is the schematic diagram of the composite wall. The composite wall consists of copper, asbestos, mild steel and aluminum. The plates having a circular cross section and the diameter of the plate is 150 mm, thickness of the plate is 6 mm. At the bottom of the composite wall, one heater is provided to give the heat input to the wall, and at the top of the composite wall, one cooling water jacket is provided to absorb the heat from the wall. Here, after giving the heat energy, heat flows along the direction of decreasing temperature, because this one is the higher temperature region, this one is the lower temperature region. Heat flows from higher temperature region to the lower temperature region. Here 7 thermocouples are provided to monitor the temperature of heater and surface temperature of the copper, asbestos, mild steel and aluminum, water inlet and outlet temperature. According to the energy balance equation, total rate of heat transfer through the composite wall is equal to the rate of heat transfer through the each plate and is equal to the total heat energy carried away by the water. So, total rate of heat transfer through the composite wall is equal to the temperature difference of the composite wall to the thermal resistance of the composite wall. Here temperature difference of the composite wall means hotter side temperature minus colder side temperature, that is T2 minus T5. Total thermal resistance means, observe here, this is the thermal resistance circuit diagram of the composite wall. This is the thermal resistance of copper, thermal resistance of asbestos, thermal resistance of mild steel and thermal resistance of aluminum. We want the total thermal resistance of the composite wall. So, that is why I am adding the each and every plate thermal resistance here. The equation comes like this. This total thermal resistance value is substituting here. Total rate of heat transfer through the composite wall is temperature difference by thermal resistance. Here each and every plate cross sectional area is a common. So, subtract the area from this thermal resistance and move that area to the numerator, and we are having another equation, total rate of heat transfer of composite wall is also written like this: overall heat transfer coefficient into area into temperature difference of the composite wall. I am equating this equation to this equation. So, observe here, area is the same for both the cases and temperature difference is the same for both the cases. Overall heat transfer coefficient U equal to 1 by LC by Kc, La by Ka, Lm by Km and L aluminum by K aluminum. This is the relation for theoretical overall heat transfer coefficient. If you want to find out the theoretical overall heat transfer coefficient, you should know the length of the each plate and thermal conductivity of the each plate. Already you know the length of the each plate because given in the specifications. You should know the thermal conductivity of the each plate. To calculate the thermal conductivity, here I am applying the Fourier law of heat conduction to the each and every plate. If you want to find out the relation of thermal conductivity, you should know the rate of heat transfer through the each. According to the energy balance equation, rate of heat transfer through the each plate is equal to the heat energy carried away by the water. Use the relation here and find out the relation of thermal conductivity of the each plate. These are the relations for the thermal conductivity of the each and every plate, and substitute these values here, we will get the theoretical overall heat transfer coefficient. After that, you have to find out the experimental overall heat transfer coefficient here. For that one, again I am applying the energy balance equation here. Total heat energy lost by the composite wall is equal to the heat energy gained by the water. This is the relation for heat energy gained by the water, and this is the relation for total heat energy lost by the composite wall. By equating these two equations, we will get the relation for experimental overall heat transfer coefficient. If you want to find out the experimental overall heat transfer coefficient and theoretical heat transfer coefficient, you should know the temperature values of the each plate and mass flow rate of the water. For that one, go for the experimentation. This is the experimental setup. It consists of heater at one end with mild steel, asbestos, aluminum and copper plates composited to form a heat flow cloth. The test pieces are covered with MS sheet guard to prevent the heat loss. One flat heater is provided at the bottom of the composite wall to give the heat input to the composite wall. At the top of the composite wall, cooling water jacket is provided to absorb the heat from the water. Here, 7 thermocouples are provided to measure the surface temperature of the heater and surface temperature of the each plate and water inlet and outlet temperatures. This one is the control panel and this is the rotameter. By using this rotameter to adjust and measure the flow of water into the cooling water jacket, and this one is the console switch and this one is the heater switch. By using this console switch, the energy is distributed throughout the panel, and this one is the dimmer stat. By using this dimmer stat, adjust the heat input to the heater, and this one is the temperature indicator and the channel selector. By using these two to monitor the temperature values at various positions of the composite wall and water inlet and outlet temperatures. Come to the operational procedure. Before starting the experiment, release the wall connected from the water reservoir and adjust the mass flow rate of the water by using the rotameter. Okay, after adjusting the mass flow rate, I am giving the power supply to the equipment. Tripper on. Switch on the console. Observe here, energy is distributed throughout the panel, and switch on the heater. By using the dimmer stat, give the some amount of the power to the heater. By using the temperature indicator and the channel selector, monitor the temperature values at various positions of the composite wall. Observe here, T1 indicates that surface temperature of the heater, and T2 indicates that surface temperature of the copper plate, and T3 indicates that surface temperature of the asbestos plate. T4 indicates that surface temperature of mild steel plate, and T5 indicates that surface temperature of aluminum plate. T6 and T7 indicates that water inlet and outlet temperatures. Observe here, the temperature values are varying with time, so the system is unsteady state condition. Wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, tabulate the values and go for the experimental calculations. These are the values recorded during the time of the experimentation after reaching the system in steady state condition. Here T1 indicates that surface temperature of the heater, T2, T3, T4, T5 indicates that surface temperatures of the each plate, T6 and T7 indicates that water inlet and outlet temperature. Initially I given the mass flow rate of the water as 0.5 liters per minute by using the rotameter. Convert this 0.5 liters per minute into the kg per second, 8.33 into 10 power minus 3 kg per second. First of all, I am calculating the theoretical overall heat transfer coefficient. This is the relation for theoretical overall heat transfer coefficient. Already we know that energy balance equation. Here I am calculating the rate of heat transfer, that means heat energy carried away by the water. Here I am substituting the values. Mass flow rate of the water as 8.33 into 10 to the power of minus 3 kg per second. Specific heat of the water as 4187 joule per kg Kelvin. Water outlet and inlet temperatures, that means T7 minus T6, 29.3 minus 26.8. Calculate this value by using the calculator. Equal to 87.1 1318 watts. This is the heat energy carried away by the water. After that, calculate the thermal conductivities of the each plate by using these relations. Substitute the all related values here. I am substituting the rate of heat flow 87.1318 into length of the plate. Already we know the length of the plate 6 mm, 0.006 divided by area, cross sectional area 0.017 into temperatures T1 minus T2, 63.4 minus 55.7. Calculate this value. 3.993 watt per meter degree centigrade. Like this, calculate all the values here. Like this, I calculated the remaining values of thermal conductivity of the each plate, substituting the all related values, and substitute the thermal conductivity of the each plate and length of the each plate in this equation. We will get the theoretical overall heat transfer coefficient. I am going to substitute here theoretical overall heat transfer coefficient here, that equal to 1 by length of the plate 0.006 meters divided by 3.993 plus length of the asbestos plate 0.006 divided by thermal conductivity of asbestos plate 2.7214 plus length of the mild steel plate 0.006 divided by thermal conductivity of the mild steel 3.9426 plus length of aluminum plate 0.006 divided by thermal conductivity of aluminum plate 8.09. Calculate this value by using the calculator. Theoretical overall heat transfer coefficient is equal to the 167.508 watt per meter square degree centigrade. Let us calculate the experimental overall heat transfer coefficient by using the relation, whatever the relations earlier we derived. This is the relation for experimental overall heat transfer coefficient. Here MW means mass of the water, Cp specific heat of the water, water outlet and inlet, that means T7 minus T6. Here A means cross sectional area of the composite wall, Th means hotter side of the composite wall, that means T2. Tc means colder side of the composite wall, that means T5. Substitute all the values here, we will get the experimental overall heat transfer coefficient 8.33 into 10 to the power of minus 3, specific heat of the water 4187 joule per kg Kelvin, T7 minus T6, that means 29.3 minus 26.8 divided by cross sectional area of the composite wall 0.017 meter square, temperature difference of the composite wall, that means T2 minus T5. Here T2 is 55.7 minus T5 is 32.8. Let us calculate this value by using the calculator. That is 223.52 watt per meter square degree centigrade. This is the experimental overall heat transfer coefficient. This is the experimental overall heat transfer coefficient and theoretical overall heat transfer coefficient value of the composite wall. Thank you.